Everything you see here will one day disappear from view, not all at once. One galaxy at a time, its light stretched beyond the cosmic horizon. Far enough into the future, the sky will hold only one remaining point of light. No constellations, no Milky Way, no dawn waiting behind the darkness. When that final star dies, the age of starlight will be over. This is the last light in the universe, including our own. Today, the sun appears eternal because human lives are brief. It warms oceans, feeds forests, holds Earth inside a river of light. Yet deep in its core, hydrogen is already becoming helium. Mass is becoming light. Every photon touching your skin is part of that slow surrender. In about 5 billion years, the hydrogen in the sun's heart will run low. The core will contract. The outer layers will swell. Our sun will become a red giant, filling the sky with fire. Long before then, Earth's oceans will vanish. Its atmosphere will escape. Our world will become a silent stone beneath a burning horizon. Then the sun will cast away its outer layers, forming a vast planetary nebula. At the center, only a white dwarf will remain. A dead star no larger than Earth, shining only because it remembers heat. Across the universe, the same ending will repeat. Stellar nurseries will empty. Galaxies will fade, one light at a time. Only the smallest red dwarfs will endure, burning with extraordinary patience. But even they are not eternal. By around 100 trillion years, the age of ordinary starlight will be coming to an end. The last natural starlight will disappear. The long sunset of the universe will end, and the age of endless darkness will begin. But the final star will not produce the final light. With its hydrogen gone, the universe will enter the degenerate era, a cosmic cemetery stretching from roughly 100 trillion years after the Big Bang to about 10 to the 40th power years. White dwarfs, neutron stars, brown dwarfs, frozen planets, and black holes will drift through galaxies that no longer shine. Yet over unimaginable intervals, gravity may still create rare accidents. Brown dwarfs could collide and ignite a brief new star. White dwarfs could merge in a thermonuclear flash. Each event will be separated by darkness longer than the present age of the universe. Even dead stars will continue to change. White dwarfs will cool toward black dwarf, objects so cold and dark that none can exist today. The universe is still far too young. Then the fate of matter itself becomes uncertain. If protons decay, planets and stellar remains will slowly dissolve into lighter particles and radiation. No proton decay has ever been observed. If protons are stable, some remnants may survive long enough to become hypothetical iron stars. But one kind of object can outlive almost everything: black holes. And in the deepest future, darkness itself may begin to glow. Black holes are not theoretical ghosts. We have watched their gravity reshape the universe. At the center of the Milky Way, stars race around something invisible, an object about 4 million times the mass of the sun. In 2022, the Event Horizon Telescope revealed the glowing ring around Sagittarius A star. It did not show the black hole itself, but the shadow it carved into the surrounding light. In 2015, LIGO detected a tremor in space-time from two black holes colliding more than 1 billion light years away. Black holes are real. They can grow, merge, and survive long after their stars are gone. In the far future, galaxies will lose stars through collisions, ejections, and decay. Their central black holes may become the last great structures left in the darkness. but a black hole appears to be a perfect prison. Once something crosses its event horizon, not even light can return. So how can the darkest objects in existence produce the universe's final glow? The answer begins where gravity meets quantum physics, and where our certainty starts to break apart. In 1974, Stephen Hawking showed that a black hole should not remain perfectly black. Around an event horizon, quantum fields in curved space can produce an extremely faint thermal glow, Hawking radiation. No astronomical black hole has ever been observed evaporating. Today, this radiation is colder and weaker than the cosmic microwave background, so most black holes absorb more energy than they lose, but the universe will continue to expand and cool. Stars will disappear. Background radiation will fade. Eventually, the balance will reverse, and black holes will begin losing mass. The process is almost impossibly slow. A black hole with the mass of the Sun may survive for around 10 to the 67th power years. The largest supermassive black holes may endure until roughly 10 to the 100th power years. For nearly all that time, the change would be invisible. But evaporation contains a strange reversal. As a black hole loses mass, it becomes hotter. As it becomes hotter, it radiates faster. After an existence longer than every star combined, its final decline will no longer be slow. The darkness will begin to burn itself away. Imagine the last massive black hole remaining in our region of the cosmos. There is no galaxy around it, no stars, no planets. For an almost endless age, its glow is weaker than darkness. Then, as its mass falls, its temperature rises. The radiation strengthens. The final stage accelerates from eternity toward an instant. In the standard semi-classical picture, the black hole releases its remaining energy in a brief, final burst. The burst will illuminate almost nothing. Space has become too vast and empty. Then the black hole is gone. Its final photons and particles spread into the expanding darkness. They may become the last significant light produced in our cosmic region, but the final instant remains unknown. Hawking's calculation eventually reaches a scale where quantum gravity becomes essential, and no complete, experimentally confirmed theory can describe what happens there. The burst may occur, or the black hole may leave something stranger behind. The last light is not a fully known event. It is the boundary between what physics can predict and what still lies beyond it. And when that light fades, the universe will not end. It will simply continue without it. After the black holes are gone, the dark era begins. Space will not become perfectly empty or reach absolute zero. Rare particles and photons will remain, drifting ever farther apart. Heat death means the useful differences in energy have almost disappeared. No stars, concentrated matter, or accessible fuel. Without those differences, nothing can power stars, chemistry, life, or complex processes. Time and expansion may continue, but almost nothing new will happen. This future assumes that dark energy continues behaving roughly as the standard cosmological model predicts. The Dark Energy Spectroscopic Instrument, DESI, has mapped millions of galaxies and quasars to measure how expansion changed across cosmic history. Its first 3 years of data strengthened hints that dark energy may evolve instead of remaining constant. That is not a discovery. The question remains open. If dark energy changes, the ultimate fate of the universe may change with it. So the path toward the last light is not a prophecy.